Hello, everyone. Thank you for joining us today for Lesson 4, Connect Your Device to the Internet. This is part of our Hello IoT series, which ran this week last week and this week. We have today's session and then one more office hour tomorrow. I will share a link to the series page where you can find all the past sessions recordings as well as register for tomorrow's office hours if you're interested. Before we start, just a few quick things to go over. Please take a few minutes, went too far, and read our code of conduct. We ask that you please be respectful to everyone, including other attendees and our speaker. We want to have a welcoming and safe environment for all. If you haven't already, please check in using our event check-in at aka.ms/reactor check-in with event ID 13424. By checking in, you will receive links to content that goes along with today's session. Please ask questions using the live chat. You should see two text boxes with a question mark over the top one. That is the live event Q&A. In the chat, I'll also be sharing some links to the Reactor Meetup page and monthly newsletters if you're interested in checking out what other sessions we have. And today's session will be added to the Reactor YouTube channel in about 24 to 48 hours. Finally, near the end, I will share a link to our Reactor survey. If you have a few minutes, we greatly appreciate your feedback. And I will now pass it over to Jim.
Awesome, thank you very much. All right, let's do the magic button to share the screen. And we're good. Right, so good morning, good afternoon, good evening, good night. Hello, everybody. Welcome to lesson 4 of IoT for Beginners. As mentioned, this is part of our Hello IoT live stream. We're now wrapping up week 2 with the 4th lesson in the series. So by way of introduction, if you haven't come to any of our earlier episodes, my name is Jim Bennett. I'm an education cloud advocate of Microsoft, which means it's my job to help folks who are interested in learning be successful with Microsoft technologies. In particular, I specialize in IoT. So if you've got any questions about learning Microsoft technologies, especially if you're a teacher, a student, anyone involved in education, feel free to reach out, get in touch, and I'll help you wherever I can. I'm all over the internet, Jim Bob Bennett, Twitter, GitHub, Instagram, LinkedIn. So please feel free to connect. Hit me up with any questions you've got, and I'll do my best to help. Now, this Hello IoT series, is based off our IoT for Beginners curricula, which is newly released. It's been out about 12 or 13 days and provides 24 lessons to get you going with IoT from the ground up. And you can find it at aka.ms/IoT-beginners. It's all on GitHub. It's a fully open source MIT licensed repo. You can clone this, you can take the lessons, you can use them in your classroom, you can use them in your study groups, you can use them for personal learning, kind of whatever you need to learn this content. And because it's free and open source, you can adjust it to suit. If you need to change the way we do it's done to teach in your classroom, you want to change some of the topics, you want to rejig the lessons, feel free. It's all there free for you to use for teaching or learning. Now, the lessons are all project-based, the idea that you build a project after each group of lessons. We're currently working through the first 4 lessons where we're building a nightlight. Over the last couple of lessons, we got our device set up and we actually were controlling an LED using a light sensor. In fact, I will show you that right now. So this is the device we built. We put this together on Monday. It's got LED, light sensor inside. If I cover the light sensor, the LED comes on. If I uncover the light sensor, get a bit of light on there, give it a few seconds, the LED goes off. Same, I cover it, and on it comes. So that's what we put together. Today we're looking at connecting this to the internet. And we're going to talk about kind of communication protocols, some sort of standard ways your device would talk over the internet with IoT services. Now, if you carry on with the rest of the lessons yourself, they'll cover projects such as digital agriculture, so where you learn to measure growth rates by monitoring temperature, soil moisture levels, to control automated watering systems and manage all that from the cloud in a secure way. We cover location tracking and visualizing GPS data and geofences for location alerts, training AI models in the cloud and then running them on the edge for fruit quality detection and stock detection on retail shelves, and then consumer devices, kind of smart timers that you control with your voice. So that's what's covered in the rest of the lessons, which obviously you can dive in yourself after this series. Now, we're running this series as a set of lesson office hours. So today we're covering, as I say, lesson 4, connecting to the internet. And then tomorrow we'll have an office hours where we can discuss anything we talked about today, or just kind of anything, do a few more demos and just kind of have a bit of fun together. Now we'll give a shout out to our friends at Seed Studios. The T in IoT stands for things, which usually refers to hardware. So shout out to our friends at Seed Studios who've made it easier to get the hardware that you need for this particular curricula. If you go to aka.ms/IoT-beginners-kit, take you to a page where you can buy hardware kits with all the hardware you need. So it's kind of a one-click place. You can say, I want, however many sets of the kits, and then Seed will ship those 4 kits to you with everything you need to be successful with this curricula. Now, one thing I will say is we've ensured that you don't have to buy any hardware. So every lesson here supports a virtual hardware setup where you simulate sensors and actuators. So you can do the entire thing without spending any money on hardware. Obviously, hardware gives you kind of a better idea of what happens, a better idea of the limitations of the hardware, the size, the weight, and you kind of see things working. But if you don't want to spend the $100 on the hardware, you can do everything for free with virtual hardware. Okay, so let's dive right in. Let's dive right into connecting your device to the internet. And we're going to talk about sending and receiving messages. We're going to connect our nightlight to an MQTT broker to allow us to connect to the internet to kind of do things with our nightlight. We're essentially going to take the same logic we've got that measures the light levels and uses that to control a light, but we're going to do it via the internet, as if we were, I don't know, lights in a stadium that used light sensors to work out when to turn on the floodlights, something like that. So why do we care about connectivity? Well, the reason we care is because of the I in IoT, and I stands for internet. IoT is the Internet of Things. It is things that connect sometimes just to each other, but usually to some form of cloud service, and they send data to the cloud. And then you have a whole IoT application backend that does analytics, reporting, analysis, AI, status storage, whatever you need to analyze the data that comes from your IoT device. That then makes decisions and then sends commands back to your IoT device to control the device. So you typically have one device, many devices, one cloud service, all the devices connect to the cloud, and then from the cloud, you have all your application logic, and they then connect back to the device. So that's kind of why you have, why you need some kind of IoT stuff. And so in this lesson, we're going to talk about some of this. We'll talk about how you send data from the device to the cloud, which we call telemetry, and then you get requests from the cloud to the device to do something, which are known as commands. And we're going to look at the MQTT communication protocol, which stands for message queuing telemetry transport. And we're going to dig into kind of telemetry, which is sensor data, and commands, which is actuator controls. So let's start with kind of the basic communication protocol that most IoT devices use. Now, this isn't like a website. Normally with a website, you make a call, you say, hit up www.bing.com, for example, and then you get back a block of data that contains the web page. IoT devices don't work like that. They don't usually make just like a REST call, an HTTP call, a web call, and get data back. Usually they work over some kind of pub-sub, publish-subscribe type mechanism. And the idea behind this is a device can publish a message to a broker, and that broker it can receive messages from loads of various different devices, from cloud services, and then forward those on to anybody who subscribes. So your IoT device would publish a telemetry message to the broker, and there'll be a cloud service that subscribes to telemetry messages, and then it will receive those telemetry messages. And then when the cloud wants to communicate with the device, it would publish some kind of command message to the broker, and then the broker would send it to any IoT devices that are subscribed to the command. So you publish messages to the broker, and you don't care what happens afterwards, and you subscribe to messages from the broker that you then respond to. Kind of everything's very much decoupled, and that way you can add 1 device, 10 devices, 1,000 devices, 1,000,000 devices, whatever, and they can all publish the broker and subscribe to message from the broker. And then same with cloud services. If you want to add new cloud services on the back end, they can all subscribe to the same set of messages or publish commands. So it's all done via pub-sub rather than any form of direct communication. It kind of allows it to scale quite well. Now, when you do pub-sub, you need kind of an agreement on how you're going to work. You need to agree how you're going to send the messages, that you're publishing and subscribing, how you subscribe to them, what the underlying technology is, all those kind of things. And there's a set of standard communication protocols that are used for devices. And MQTT, message securing telemetry transport, is probably the most famous pub/sub protocol for IoT devices. You research IoT, you'll see MQTT coming up a lot. MQTT is originally invented by IBM, designed to monitor oil pipelines. It's kind of a low bandwidth, small data packets designed to send lots of data very fast with slow internet connections. And it was designed in 1999 to monitor oil pipelines, and then open sourced released as an open standard about 15 years later, or by IBM, which is very cool. So MQTT is standard. You will see others. So sometimes you get AMQP, which is a more advanced message queuing protocol. Sometimes you do it over web requests, which involves a bit of jiggery-pokery where you would send a message by making a web request, and then you would poll. So the way you would subscribe is by constantly polling, saying, do I have a message? Do I have a message? Do I have a message? Which is less efficient, but allows you to work in places where you can only make HTTP calls because of firewalls or things like that. So MQTT, message queuing telemetry transport, let's say the most popular pub/sub mechanism for IoT devices. There's loads of MQTT brokers out there, loads of open source implementations of this. The idea of this is you have a single broker, and then you have multiple clients that connect with named topics. So you would publish to a topic that has a name, and then something else would subscribe to a topic that has that name. And everything's routed via topics. The broker doesn't care what's connected, how many devices, it's all based off topics. So for example, you create a topic called Telemetry, and your IoT device would send a message to the telemetry topic, and then the cloud would subscribe to the telemetry topic and pick up those new telemetry events. So you would send soil moisture or temperature or light to the telemetry topic, and then on the other side, the cloud would then subscribe to that and pull off those values. Same as if you wanted to send commands from the cloud back to the device, same thing, you publish your commands topic, the IoT device would subscribe to that topic. And that way you scale by just adding more subscribers to the topic. If you have 100 subscribers on the telemetry topic, then all 100 will receive each message. It's not a case of one message goes to one recipient, it's one message goes to all recipients. You could have 1 million devices listening on the commands topic, one cloud service pushes a message to the commands topic, all 1 million devices will get that. So everything's routed via the topics. It's all done using TCP/IP, so it's all done using a standard network stack under the hood, which is quite nice because it works on devices that support TCP/IP, which is most Wi-Fi connected or Ethernet connected IoT devices. Now, question for you to think about, we can discuss this in the office hours tomorrow, is scale. What if you have a lot of messages? We're sending all these messages in MQTT broker. What happens if you have a lot of devices, if you have 1 million devices? So how can you make sure your MQTT broker can handle all of this? So something to think about kind of scaling. In IoT, when we're kind of playing as developers, we'll put together 1 or 2 devices, send data to the cloud. We don't normally think about scaling. But if you're rolling this up, if your IoT device gets hugely successful and you've suddenly got 1 million devices, how do you scale that? How do you deal with all the messages? So something to think about, so we can talk about this in the office hours tomorrow. So how do you connect? Well, you start off by connecting your device to the internet. You need an internet connection. So you need an IoT device that's got something like Wi-Fi, and then you can connect to an MQTT broker that's running somewhere. Now, you don't actually need to set up your own MQTT broker, which is quite nice. There are plenty of free ones available over the internet that you can use for quick testing. So one of them is Mosquito. So the Eclipse Foundation have released a MQTT server and broker called Eclipse Mosquito. Notice it's spelt with 2 T's because MQTT. So if you ever write about this, you'll get your spell checker complaining. But this is an open source MQTT broker that follows the standard MQTT protocols that IBM open sourced. And you can get all the source code you need for client libraries, server libraries, the whole lot, and they host a MQTT broker. So this is public, it's running, and you can use this to test out MQTT. You can send data to it, get data back. And what's quite nice is it supports a load of different variants, including encrypted, unencrypted, unauthenticated, and they've got things like ones with a server certificate that's expired, so you can kind of test all your certificate logic, things like that. And it's free for anyone to use. Now, this is great. This is a fantastic way to kind of get playing and get started with MQTT. But obviously this is free and this is public, which means it's not guaranteed to be running. It's not guaranteed to support any volume of traffic, and it's public, so everybody can read any messages you publish to this. This is fine to use to get set up just for playing, to learn MQTT, but you would never, ever, 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 ever use this for any form of production environment, because it's not guaranteed. You know, they run this on I think it's just one machine that it runs on an Intel Atom powered device, and anybody can subscribe and pull off your data. So, but it's good for playing. It's a good way to get started with. Saves you setting up an MQTT broker yourself. Can you send messages to another IoT device through MQTT? Yes, yes you can. It doesn't care what connects. Anything can subscribe, anything can publish. So if you wanted one IoT device to send a message to the cloud, it would send it to a topic that the cloud is listening to. If you want to send it to another IoT device, it just needs to send it to a topic that other IoT device is listening to. So if you wanted to use it for device-to-device communication without routing all the way through a cloud service, you could just have a topic of /device communication, for example, and then you send it to that. Now, what you can do with these topics, we will look at this a bit more and a bit later on, but you can actually have specialist topic names, and you can send to routes of topics or very specific topics. So if you want to just do one device to one device, you would have a topic name that's got like a device ID in it, so you could just get one message going from one to the other. But yeah, great question. Devices can definitely talk to each other over MQTT. Literally, it doesn't care what publishes or what subscribes. It's just a pipe. And IoT devices can put on and subscribe at the same time. Clouds, you can use it for cloud communications, absolutely anything talking to anything. Great question, great question. Okay, so let's do a bit of code. Let's actually get our device connected to the Eclipse MQTT server. Now, this is where it gets fun with Arduino libraries, because we have to do a little bit of work to get all this working. This device, the Wii terminal, it does have, I believe there's that little bit in there, a Wi-Fi chip in here, so it can connect to the internet, but obviously we're going to have to do some setup. This is a Arduino device. You know, things don't just go as easy as we would like. That's the way kind of microcontrollers work, is you often have to do a little bit of hard work to get everything going. Another question. Does IoT device manage the transient issues while connecting to topics on the broker? So that's all up. It's your code, so you have to worry about that yourself. So the question about this is, things like if the connectivity drops out, does your IoT device manage it? And that depends on the library that you're using. Some libraries will handle this for you, other libraries won't, so you have to handle that yourself. We will be looking into, we'll do a deeper dive in a second where we kind of talk some more about some of those issues. But you have to make sure you handle it, and that's either by picking a library that does it for you or doing that yourself. If you move to more advanced cloud services, one example is Azure IoT Hub. That's kind of a more managed cloud IoT service that you can connect over MQTT under the hood, and the libraries that come for Azure IoT will handle things like reconnections, retries, things like that. Whereas a basic MQTT library, you have to write that logic yourself. Great question. It's really good to think about that, because connectivity is never ever guaranteed. And there's a great story said about connectivity. There's a great story. I will show you a picture. It's not included in the slide deck for this lesson, but it is one from this lesson. I'll show a great picture. Here is a Ferrari, and you can't drive it. Somebody drove it into a parking garage, and it started to, kicked off. There's a firmware upgrade. They started to do the firmware upgrade, but there was no cell signals. There's no connectivity, and that bricked their car. So it meant they couldn't actually drive their $100,000 Ferrari. they had to get somebody from Ferrari to come out and fix the problem. So yes, lack of connectivity bites all of us. You need to make sure your code is resilient to a lack of connectivity. Great question. Okay, so let's start by getting our Arduino device connected to Wi-Fi, connected to the internet. Now, one of the reasons I love Platform IO as a tool for programming microcontrollers is the way it manages libraries. The Arduino IDE, it has a library manager. You can kind of add libraries, but you don't know what library something needs. Somebody has to say to you, to run this sketch, you have to import these libraries. The way that Platform IO does it is with an ini file where you tell it what libraries you want. So what I can do is I can grab this, drop this code in there, and this tells me to tells the project that needs the Wi-Fi libraries and a few other bits and pieces to be able to connect to the use the Wi-Fi chip to connect to my Wi-Fi and connect to the internet. We need a library that works with MQTT, and this pub/sub client is a fantastic one that allows you to kind of get going pretty quickly, connecting over MQTT and sending data. So the next thing we need to do is actually make a Wi-Fi connection from the device. It's not like a Raspberry Pi where you set up the network connection at the start and it's kind of there, just like on a desktop or laptop computer. You have to explicitly set up your Wi-Fi in your firmware. So the first thing I add is a config file. And then to this config file, I'm going to just add a bit of code. And then we have to define my SSID and password. So I've set up a temporary Wi-Fi with the super secure guest SSID and password as the password. Don't worry, I'm being safe. This is all isolated from the rest of my network. But I need to define that in here. I need to actually hard code my values, either in my code or certain devices have encryption chips that you can kind of flash, and that saves these in a secure chip on your code. It's probably more advisable to use some kind of secure chip on your board. But obviously for getting this working, I'm just going to type it in here. And then we'll go back to my main file. This is the code we had before that sets up the serial connection, sets up the light sensor pin for input and the LED pin for output, checks the light values, and turns the light on or off. Just going to add a few more enclosed directives here to bring in the Wi-Fi bits and pieces, our config file and the pub/sub client. Going to add a function to connect Wi-Fi. So this will then, if we're not connected, it'll start the Wi-Fi on the SSID and password, and then wait half a second and just keep retrying until we're connected. And then in my setup method, I'll make the connection. So this will now connect to Wi-Fi. Now, to be truly resilient in my loop, I should be rechecking my Wi-Fi and then connecting if we lose connection. But yeah, this is just for demo purposes, so I'm just going to connect once. In theory now, if I now upload this to my device, it should hopefully connect to my Wi-Fi. You'll see it's taken a long time to build. It's pulled down the libraries. The libraries that I've added in here, all these libraries, it actually imports them as source code. So if you go in here, you'll see you've got all the source code. It literally grabs them from a GitHub repo and drops the source code in. So it has to compile that source code. And assume the libraries don't change, it'll keep cached versions, and then we only need to compile it once. So the next build will be much quicker. So that's done, and then connection to Wi-Fi. Connected. So we're now connected to Wi-Fi. We've had to bring in the Wi-Fi libraries and then set up our SSID and password and then write the code to connect to Wi-Fi. Now, so this is what I love about Platform IO. I can literally copy and paste this in. If I were to give you this code, it would know what libraries you need to bring in, so it makes it much quicker. So that's got us connected to Wi-Fi. Next, we need to actually connect to MQTT. Now, when you connect to test.mosquito.org, you need to have a unique ID. Every device that connects to an MQTT broker needs a unique ID, so it can identify itself and subscribe. And if you have a non-unique ID, you'll get a connection error. So I normally just use a GUID. So I use something like guidgen.com to generate a GUID, and that gives me an ID. I then have my broker, test.mosquito.org. That's what we're going to connect to. That's this public broker here. and then I build up the name of my client, which is my unique ID plus my client. So that's kind of what I need to kind of define the things I need to define to identify myself. Now I need to connect. So I'm just going to define a couple of variables here. First is a Wi-Fi client. So the way you connect with Arduino is you need to actually have a Wi-Fi client that provides the underlying socket connectivity over your Wi-Fi, and then you put some form of protocol-specific client on top of that. So in this case, I've got a PubSub client, MQTT client, but you can also get like an HTTP client if you're making web requests, or other kind of clients that will sit on top and wrap the underlying Wi-Fi connection. Then I need to actually add the code to connect. So I've got this reconnect MQTT client method, and that simply says if we're not connected, connect using my client name, dump out the connected, otherwise retry after 5 seconds. And that will just keep on trying to connect. Now, connections to MQTT clients, they can drop out, especially the test connection. So we need to make sure that we keep retrying. In the loop, we want to make sure if we're not connected, we retry. Then we need our initial connection, where we set up our server, our broker. This is test.mosquito.org, and we connect on port 1883. So if you've done much internet programming before, you'll know things like HTTP, you connect on port 80, HTTPS is port 443. These are just kind of different things that are different ports you listen on. 1883 is MQTT, unencrypted, unauthenticated. That's what we're connected to. We're not authenticating, we're not encrypting. If I wanted to use encrypted, I would need a certificate, and I can get to a different port. If I wanted to authenticate, I connect on a different port. But this allows me just for playing, I'm just connecting, and I'm just going to pull back, and I just don't care about security at this point. Obviously, very bad thing to do, not care, but I'm just using this to demo how to connect to MQTT. Then once I'm done, I can then create my MQTT client in my setup. So that allows me to create the MQTT client, gets me connected, and then in my loop, I'm just going to replace all my loop logic here because we'll eventually be building the server side. In my loop, I'll reconnect just to double check them connected, and then I call client.loop. Now this is very, very important because Arduino devices are not multi-threaded. If you want to have multiple threads running, multiple threads of execution running at the same time, you need to use some kind of real-time operating system or some kind of threading library that implements this. So what that means is, if a message is received, so somebody posts a message that I'm subscribing to, there is no thread of execution that will pick up that message. So you have to call this loop function, and this will then tell the MQTT library to pull any messages off the network that it needs, so to handle any subscriptions. And so when I send a message, I'll write explicit code to send it, and that'll get sent. But to subscribe, I have to, in my loop, call loop, and that will constantly poll the MQTT network libraries for any messages that are being received. Now, I could use more advanced boards. I could use a real-time operating system that provides multi-threading and have a background thread that this runs in. But this is very simple Arduino code, doesn't have multiple threading, so I have to call loop just to kind of poll for more messages coming in. And that's what I need to do to get connected. So if I now upload this to my device, you see that compiled much quicker because it didn't need to compile all the Arduino libraries again. There you go. We're now connected. So we've connected to the MQTT client. That's got that connection going. Okay, so let's dive a bit deeper into MQTT and kind of go more over the great question about transit issues. Next question. If each IoT device is a client, how does the registration of clients manage for large volume of IoT devices in an environment? So a lot of this depends on how you are actually connecting. So I mean, this what I'm showing here is just using MQTT. It's just we're just going to send and receive messages, and we identify using a unique ID. So the ID I specified here, this is a unique ID for the device, and that's how each device would be identified. In terms of registering large numbers of clients, again, that depends on how you're going to be building your IoT solution. You probably wouldn't just use an MQTT broker. You probably would use a managed IoT solution, and these managed IoT solutions usually handle a lot of registration. For example, I use the Microsoft one as an example because we're Microsoft, I might as well. Microsoft has Azure IoT Hub, which is a cloud service that your device connects to, and it can connect using MQTT, AMQP, or HTTP if you want to, and you can send, and that service allows you to send messages back and forward. And that device registration, in its most simplest, you will literally say to IoT Hub, I want to create a device, and you'll get back a connection string for that device, and the device would use that. So you can start by managing it manually. Create device, create device, create device. There's also a thing called device registration service, where you can configure how devices could automatically register themselves. So if you've got a big consumer IoT device, you're rolling out 1 million devices, you would put some form of secret key in an encrypted chip on the board, and that device would then connect to Azure IoT Hub, to the device provisioning service it's called, and say, this is my encrypted, this is my special ID, I want to register myself, and it would get automatically registered in the IoT service and then send back a connection string to connect in an authenticated way. So yeah, for absolute large volume, you would have some form of secret on the device that would allow it to connect. Another option would be you could manually manage the registration. So you'll see some IoT devices have a Wi-Fi hotspot, and you would connect from your phone and you would register, create an account. What would happen then is the web service you hit from your phone app would then do the device registration for you on the cloud side, and then push a connection string back to your phone, which then get pushed to the device then uses to connect and authenticate. So kind of a number of different ways, but most of the cloud providers that provide an IoT service provide some form of registration capability that you can do at scale. Obviously, if you want to do it all yourself, if you want to do an MQTT broker, you would then need to manage that, build that management logic yourself. But yeah, cloud services do a lot of that for you. On the Azure side, device provisioning service is the service that does all this. Great question, really important question, because it's, as I was saying earlier, it's not about 1 or 2 devices. It's when you scale, when you're dealing with 1,000, 1 million devices, how do you manage that level of scale? And things like device registration is one of the tricky parts. So great question. Okay, so let's just dive a little bit into MQTT, and then MPT, come back to your question about transient issues. So MQTT topics, one thing is they can have a hierarchy. What that means is you can have a top level topic, subtopic, 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 kind of like the folders on your computer. So it'd be /telemetry/ something. So for example, if I had a device sending 2 separate telemetry messages, one for humidity, one for temperature, I could send it to /telemetry/humidity, /telemetry/temperature. And so that would send it on a subtopic. I could then subscribe to either /telemetry/humidity or /telemetry/temperature, and that way I would get just the specific messages, or I could subscribe to /telemetry/star. I could use a wildcard, and that way I would get all the messages from all the subtopics. So anything gets published to /telemetry, I would receive. And so you would kind of, if you had, say, I don't know, a big set of industrial machines, and you had a vibration sensor, a temperature sensor, you would probably have your vibration sensor publishing to /telemetry/vibration, temperature sensor /telemetry/temperature, and your cloud service would subscribe to /telemetry/star, and that would pull all the data back and then analyze it. And then if you wanted to add, say, a sound sensor, that would publish to /telemetry/sound, but that would still be detected by your cloud service because it'd be the cloud service listening on the wildcard. So that kind of allows you to be very specific with sending messages from a device and then receive them in a very generalized way. And the advantage of these topics as well is if you wanted to do device-to-device communication, or you want to communicate with a specific device, you could use the device ID as the topic. So you could subscribe to /messages/device47, and then any messages sent to device 47 will be picked up by your device. And if there's any messages need to get sent to all devices, you can also subscribe to the wildcard. It kind of gives you a lot of flexibility in how you define how you send and receive your messages. Messages also have what's called quality of service, and this determines the guarantee of the message being received. Obviously, a lot of this is it doesn't guarantee the message is received, it's guaranteed that you know about the message being received. So the most basic one is fire and forget. No guarantee. Send a message, I don't care what happens to it. I don't care whether it gets the broker, what have you, I don't care. The next one is at least once. So you need to get acknowledgement that it's been delivered. So it will just keep retrying it. It'll keep saying, send the message, send the message, send the message, send the message. And when it gets back a response, say, I've got the message, it'll stop. But obviously that means you could end up with multiple messages. So I could send, get acknowledgement to the first message, get acknowledgement the second, the third, the fourth. So you could end up with multiple messages being sent. So if you're going for at least once, then you need to make sure that your code can handle multiple messages of the same. And then you get exactly once. And so it's kind of a two-level handshake. Send the message, wait for acknowledgement. Didn't get acknowledgement, message didn't get sent. So you kind of use all these different mechanisms to guarantee how the message is being sent, to work out how it all depends on how important your messages are and what you care about. Things like telemetry, it's probably fire and forget, because if you're sending a message every second, if the service is down for say a minute, it probably doesn't care about the last 60 seconds worth of data. It just cares about the current value. So you can probably do telemetry fire and forget. Commands to do something like turn off a heating system, you probably want assured delivery because you want to make sure it actually happened. Or you could do maybe acknowledge delivery, because it doesn't matter if you say turn off 10 times, once it's off, it's off. So you kind of need to work out which kind of quality of service you would need. Now, one thing to note as well, just think about the whole quality of service thing, is the queue part of MQTT stands for the word queue, but it's not actually a queue, in that the messages do not build up if they're not being pulled off. So once a message is there, if a client disconnects, then reconnects, it may not get the messages. So any message. So if you subscribe to say the /telemetry topic, you go down for a minute. Any message sent to /telemetry in that minute, you will not receive when you reconnect. Now you can have settings on messages to retain them, so that the last message is always saved. So that if I send 10 telemetry messages, when I'm offline, when I reconnect, I'll always get the last one. So you can do that. So that if someone subscribes, they don't lose the last message. You can keep a live code that constantly checks to make sure you're alive, so you don't lose connectivity. But it's some options, but you really have to kind of build that logic in yourself. So if it's really important that you keep the messages, that queuing capability is really important, you may need to do something yourself. You may need to potentially use a different technology, rely on acknowledged delivery, something like that. So you kind of had to build that in yourself. Okay, so let's take a moment to talk about telemetry. A little bit of historical data. The word telemetry is Greek, and it means to measure remotely. Telemetry. Metry, metering, part of measuring. Tele, you might be able to know telephone, long distance for speaking. Television, long distance vision. Telemetry is remote long distance measurements. And it's the word we use for measuring data from sensors and sending that to the cloud. Another useful historic note might find interesting. The very first telemetry was invented in France back in 1874, and they used it to measure snow depths on Mont Blanc from Paris. So they want to make sure there's enough snow for either crossing the mountains or going skiing. That was back in 1874. That was done using physical wires. They didn't obviously have Wi-Fi back in the day. It was literally long cables from Mont Blanc to Paris for measuring snow depth. MPD asks, does synchronous communication need to be handled in each IoT device logic? Yes, so you need to make sure there's logic either in the library you're using or on your device for kind of handling that communication, making sure the messages are received, or the acknowledgements there. So a lot of it can be provided by the libraries, depends on which library you're using, which service you're using. And there are multiple different techniques you can use for managing things like this. For example, again, picking Azure IoT Hub as one example. If you can set up commands to retry. So if you send a message from the device, from the cloud to the device, it'll just keep retrying. If the device is not connected, it will wait, and then as soon as the device connects, it will send it again. You can keep data synchronized using something called device twins, which are JSON documents that kind of kept in sync client and server. So there are different techniques you can use. It all depends on which backend library you're using, which libraries you're using, which kind of cloud service you're using to do it. But yeah, you need to make sure either your library does it or you have that logic in there to handle all that. So telemetry example, you think about our thermostat idea. You would gather telemetry data and then publish up to the cloud. The cloud then analyze that telemetry and adjust your thermostat. So think about, like, I mean, my temperatures, my thermostat setup that I've got here, I've got thermostat in my hallway, temperature sensor in my bedroom, living room, upstairs hallway, and they would send different data. So I would have some telemetry from all those different thermostats. It would probably send it as 3 different values, 3 or 4 different values inside the telemetry message, and then my cloud service would then look at that and then try and work out what decision it needs to make based off those 3 values. So bring all the telemetry together, send it, using some kind of JSON in a message. So let's actually do it. Let's actually send the light level to MQTT and then have a quick look at putting that data off. So if I zip back to my code here, and first thing I need to do, I actually need some JSON to generate all this. Sending messages in JSON, and with Arduino, there's a library called Arduino JSON for handling JSON. I also want to pick the topic I'm going to send to. So I'm going to use my ID/telemetry. This topic should be unique because this is a public MQTT server and everybody else is going to be publishing it. So if I have a topic called telemetry, probably other people are using it. So I'm going to put my unique ID in there with telemetry just because it's public. Okay, and then let's actually build up some stuff. So I need my Arduino JSON header file so I can build some JSON. And then in my loop function, that way, got a bit of code here, builds a JSON document using Arduino JSON with my light levels that it gets from the light sensor, and then it'll publish it to MQTT. And that's kind of all I need here. This is kind of slightly complicated code because we're building up dynamic objects, which C++ is not so great on. And then we print out to serial monitor what we're sending, and then we actually just publish it. So that's our kind of basic publishing. And let's upload this, and that will get going uploading that. And in a second, we'll actually see it all publishing. There we go. Had to recompile everything because bringing in new libraries, so potentially new dependencies and defines and all that. So there we go. Done. Uploaded. Get to the Wi-Fi. Done. And that telemetry is now going to the MQTT broker. So that telemetry is being sent. So let's look at receiving it. Let's look at the other side, actually subscribing to the telemetry. And so for that, we need some kind of server code that will actually listen on the other side of subscribe. It's pub sub, we're publishing, we need to sub, we need to subscribe. So we need to write some code to actually subscribe the other end. So I'm going to do that just using a bit of local Python code. So I'm just going to spin up another VS Code. And let's knock up a little bit of Python code for doing this. So let's just create a folder for this. Let's call it Nightlight Server. Let's call it that. And then let's just open that in VS Code. Now, so write this in Python just because it's easier than writing a local one in C++, because I'm not insane trying to write local C++ code. So let's create a file called app.py because we want Python, and then let's create a Python virtual environment. If you've not done Python before, virtual environment is kind of a way to get a local version of Python with a whole lot of local libraries installed, that when you install a library, it stays local to that environment. It's not installed globally. So, in fact, you know, let's just. So, virtual environment there. There we go. Now, in terms of actually using MQTT, there's a Python package called Parho MQTT. That is actually referred to, if I zip back here, Eclipse has Parho, recommends Parho for the client library. So this is kind of a good bit of a good Python client library we can use for connecting to MQTT. And then let's grab some code. Now, the first thing I need is an ID. Now, this ID, I'm going to use the same one as I'm using here in my device code. So that way I'm listening on exactly the same topic. I'm listening on the ID/telemetry, the same one we're publishing to. My client name is Nightlight Server rather than Nightlight Clients because it's a different name. And this will then connect to MQTT and then listen for telemetry and print that out. So, oh, we lost our MQTT connection. That happens sometimes. Hence why we reconnect every now and again. Let's just turn it off and turn it back on again. See if that fixes the connection. So while that's running, just going to run this Python code. There you go. So that's now picking up messages. So if we look here, we're publishing, sending telemetry from my device, 120, 119, cover that up, 5, uncover it. 122, 120, there we go. So we've got data, it's coming from our client and it's going to our server code. Now, obviously I'm running this locally just to kind of demonstrate how this works. Your server code could run in the cloud or on your data center, kind of whatever, but that's data going back and forward. So I've now got telemetry. So just showing again, I published to this unique ID/telemetry. And then over here, I subscribed to the same ID/telemetry, so it's a different topic. Obviously, if I wanted to publish something more detailed, I could publish here to /telemetry/light. And then over here, I could subscribe to /telemetry/light or /telemetry/star to get everything, kind of whatever I need. My MQTT client still connects to test.mqtt.org. This has got a loop start. So Python runs multi-threaded on my laptop, so I can just click at the start, and this is the same kind of polling that I'm doing with my loop call in my loop function on my Arduino device, but this is run on a background thread, which is quite nice. And then we subscribe to the topic, and when we get a message, we call this function, which just dumps it out. So that's kind of showing telemetry in action, going from device to the server. So we're internet connected now. So that's what we did. So how often should telemetry be sent? This is kind of one of those difficult questions of how much data to send. If you were here for my first episode, we talked about how there reckons to be 80 zettabytes of data a year being produced, and most of that will be wasted. So how much data should you send? Depends, completely depends on what you need. Yeah, the more data you send, the more data you have, but that uses more resources. And might be completely unnecessary. You might be using bandwidth, cloud usage, you might be using storage for absolutely no reason. You know, if like a thermostat in my house, for example, there's no point in sending the temperature to the cloud every second. Why? It's not going to change that often. Temperature doesn't change every second. Once a day is probably too little because it's cold at night, it's warm during the day, I want to adjust it. So maybe every few minutes, 5 minutes, 10 minutes, maybe might send that. If anything's mission critical, it's better to be safe than sorry and go over the top. If you're measuring vibration on machinery for predictive analytics to turn the machine off if it's going wrong, you probably want to send it way too often. But you also may want to think about edge devices. So if you need to gather that much data for processing, and most of the data is going to be wasted, you just want to catch those anomalies to work out your machine's about to break, you may want to run that on an edge device, which will then monitor that and just send the telemetry to the cloud when there's a big change. Yeah, you could have a filter that simply says measure every second, but only send to cloud when the value changes, something like that. So really it depends. It's kind of one of the design things of your IoT application is how frequently you should send the data. Same with loss of connectivity. What do you do with it? Do you care? Do you need to store the values? Should your IoT device store all the temperature values and then send them to the cloud? If all you care about is turning your heating system on and off, probably not. If you want to do analytics on the data, then you probably do want to send it. So again, it depends on your use case. You have to work out what you need to do with that data, because internet outages happen, things drop out, Wi-Fi drops out. I'm using a particular huge internet vendor for my internet here. It's the only one around. They have a monopoly and they drop out quite a lot. It happens. Wi-Fi is definitely not guaranteed. Ask the owner of that Ferrari in the garage. So you have to make sure you work out what you need with your data, and things like MQTT won't do a lot of this for you. You have to kind of manage this yourself. Okay, so sending commands. How can we kind of change our logic a bit to send a command from our device? How can we command the device? So command is a message, usually from the cloud to the device, to say do something. Telemetry is here's some sensor data. Command is do something with the actuator. Reboot yourself, reinstall some firmware. It tells the device to do things. It's usually telemetry, sensor data from the device to the cloud, commands from the cloud to the device to tell it to do something. You probably have a different topic that you'd use for a command. It's sent the same as a telemetry message. It's just the intent of the message is to tell you to do something. It's sent exactly the same. It's just the intent is different. So let's actually do that. Let's use a command to handle our light control. So rather than have the light logic being put inside in here to turn the light on and off, let's actually control it over the cloud. So what I'm going to do, I'm going to define another topic. This is the topic I'm going to publish commands on. Sent exactly the same as telemetry. It's just a message to a topic, but the intent is to command something to do something. And then what we're going to do in our handle telemetry function, we're going to build a command that turns the LED on, set it to be 100 because it's quite dark in this room right now. If the light is less than 100, we send LED on as true, otherwise we send it as false, and we publish this to our server command topic. So we've now got light control logic in the cloud. And then what I'm going to do is write some logic on the Arduino device to handle that. So same thing again, I need my command topic. So this is the topic we're going to listen to get commands. I'm then going to add a line to subscribe. So in the reconnect method, once we're connected, I'll make sure we're subscribed to the command topic. Once we're subscribed, we use a callback. So in the Python code I wrote here, we have this message callback handle telemetry. We need to do the same thing in Arduino code. We create a callback. This gets called whenever we'll set this up to be called whenever a message is received by the MQTT client, and this will take the payload that comes in as a uint8_t, because that's how they picked up wanted to do it, convert that to a string, convert that to a JSON document, get the value of the LED on, and then if it's on, we write the high to turn the LED on. If it's off, we write a low value. So depending on the true or false value that comes back, we control the LED. Then when we create, we need to set the callback. So this set callback just simply means every time we're subscribed to a message, when the message comes in, call this callback function. Now, you see that the callback takes the topic. So every message on every topic always comes into this function. So we would have to write filter logic in here to filter depending on the different topics. We've only got one topic, we don't care, we can just handle that one. But if I had multiple topics, I would have to handle them in this client callback. And that's basically all I need to do here. So if I upload this, let this build and do its thing. Cool. So that's going to connect to Wi-Fi, connect to MQTT broker. Telemetry's going over. Go back over here. Let me just restart my app, the new logic. So you see we received message light 121, sending message LED on false. Go back here, receive message LED on false. So it's getting back the false messages. So if I now cover this up so it's darker, you'll see we've now got receive message light 5 LED on true. Eventually that message will be picked up by the client. It's not the fastest because this is, say, running over the internet to a public MQTT broker that's running on a very low powered machine because it's free. Eventually we'll receive the LED on true message. Give that a few seconds. There we go. LED on true has been received, and you'll see my LED is now on. Now, obviously, this is not the fastest. You wouldn't use this for instantaneous feedback. Not great for a night light that goes outside my 8-year-old's bedroom. But if I was, say, monitoring the light levels in a stadium to control big floodlights, this would be quick enough. But you probably use some kind of managed service that's a lot quicker than a free device that you're connecting to. So we've built the connectivity. We've actually got the logic in the cloud. We've got IoT device, gathers sensor data, publishes it to a telemetry topic, some server code, reads the telemetry topic, makes a decision on that, publishes that back to a command topic. IoT device picks up the command topic and uses that to control the LED. So question, MQTT always maintain the connection to the broker, or it depends on the configuration? So the connection can drop, and it's kind of up to you to make sure that the connection keeps retrying. So what I've got in my Arduino code in my loop is reconnect. It's constantly check the connection, check the connection, check the connection, check the connection, because this particular library that I'm using doesn't check the connection. On the Python side, I'm not checking the connection because the Paho MQTT library handles that loss of connectivity and reconnection for you. So it depends on the library code you're using. You need to make sure you understand your library and then reconnect if you need to. Wi-Fi is flaky, internet is flaky, all these things can go down. So you need to understand your client library and make sure that connectivity is managed for you. If you've used something like an IoT Hub, for example, the Azure service, that will manage that connectivity for you. That kind of keep you connected. You just have to manage the underlying network connection. So it depends very much on your library and what you're using. But yeah, great question. Connectivity is important to consider. You don't want to just connect once in your setup method, lose connectivity and then never connect again, and somebody has to physically reboot the device. It's a great question. So yeah, what should my service do if IoT device unreachable? Again, it depends. You need to work out what you need to do. Do your commands need to be processed in order? So do you queue up your commands, then resend them? If your command is turn the LED on, turn the LED off, you can probably just ignore them except the last command. So kind of very much like with telemetry, it depends on what you want to do with it. So a little bit of a challenge for you, something to think about. We can talk about tomorrow's office hours. I've asked you before to think about the IoT devices in your home. Now think about what messages they might send, what messages they might receive. In terms of connectivity, what telemetry, what commands are being sent? Are they secure? Very important question. Are they secure? This data that they're capturing, is it secure? So what does it capture? What kind of data about your house does it capture? How is it available to people? So think about, and we can talk about this in the office hours tomorrow. So thank you very much. That is lesson 4, connect your device to the internet. We've seen over the past 4 lessons, we've learned about the Internet of Things, learned about dev kits and sensors and actuators and internet connectivity. We've configured an Arduino device. We've got it acting as a nightlight. We connect it to the cloud today for an internet-controlled nightlight. In our office hours, I've done the same kind of setup with Raspberry Pis and our virtual IT hardware. Tomorrow's office hours, I will recreate the same MQTT demo with a Raspberry Pi and virtual IT device. But yeah, this is kind of the end of the lesson part of the series. Tomorrow says office hours. It's an ask me anything. I'll do a few demos like this MQTT setup with a Pi and a virtual IT device. But otherwise, bring your questions and we can kind of discuss more some of the discussion points from today's lesson, and then I can answer any of your questions. And so with that, I will wrap up. Thank you very much, everybody, for your time. Really appreciate you coming in and joining me for this. And I will see you all. Hopefully tomorrow. So take care and enjoy the rest of your day.
Thank you.